Good Tuesday to you, everybody in Gov 603. Welcome to week, boom, 3. Hey, you made it. Other side of modular week. And we are now, 5, 6 weeks away from the end of the semester. All right, that's pretty good. So you need to stay focused, stay motivated, or in my case, stay caffeinated. Oh, much better. And who do we have here today? Which cup? Oh, yes, this University of Missouri Department of Geography over spring break or modular week or whatever you like. I did a writing workshop and guest lecture sponsored by the Geography Department. You might be saying, that's weird. Why would the Geography Department be doing anything that concerns writing? Well, there's a branch of geography that's real close to ethnography, and that is it tries to figure out, you know, why do people do what they do within certain groups, which is not that dissimilar to what we do in political science. It is we're asking, why do people behave the way they behave within certain groups? So, there's sort of, it may not be apples to apples, but it's apples to oranges. They're in the same food group. Okay. Before we get to your questions from week 8, a couple of pieces of housekeeping. The test was graded way back. That is your midterm exam. You should be able to see your results, and I've turned those on. There was one question, and it concerned the n value, and I felt that I wasn't clear enough in asking it. I had included just an uppercase n, and I could see from your responses that some people may have been confused and wondered if I meant and large N meaning the general populace, as opposed to small n meaning the sample that you're dealing with from the general populace. So if you got that question right, you got it right. If you got it wrong, I went ahead and went back and gave you points for it anyway. My mistake. Sorry for the confusion. Otherwise, in general, people did pretty well. If you have any questions about why the questions were the way they were, boom, shoot it to me by way of email. Okay. Also, your papers are graded and done. Now, if you have a note on your paper, so check, go in and check your work that I've completed. You should get an email too when I send a comment to you. But if there's a note on there suggesting that we connect, let's connect. Okay, connect by phone. Excuse me. Now, remember what we're doing here. Nobody's in trouble. There's no punitive anything. That we break the paper into 2 pieces so we can work on our professional development, our development as thinkers, as researchers, and as writers. Okay. And so I'm trying to help you. I'm trying to give you feedback. If you don't have a note that says connect with me, the other thing that I want you to make sure that you do, you may notice that after 2 or 3 pages in a section that there aren't any more remarks on the pages throughout that section. Okay. The reason for that is it's not that I haven't read them, or it's not that everything on there is absolutely just fine, but I'm looking for patterns. I mean, yes, you must read carefully for typographical errors. That's just fundamental. But I'm looking for patterns in how you conduct your research and how you structure your paper. And when you look at my remarks, please look for similar issues throughout the rest of the paper, whether I've made a comment on that page or not. Okay, that's up to you. Now, remember what we're doing here. We're doing one paper in 2 parts, not 2 papers, one paper in 2 parts. So the first bit, I've tried to give you some feedback about how you're doing as a writer, as a researcher, as a thinker. Go to the assignment folder in Blackboard, and you will find the instructional sheet for part 2, which is the completion of the paper. Okay, follow those directions carefully, and then the due date is April 21st. So you've got a month and change. If you have any questions about what I wrote by way of comment, even if I didn't ask, maybe we could talk. Please send me an email, or Monday, Wednesday, Friday, my office hours between noon and 2 now Eastern Daylight Time. We only hang on to this stupid daylight savings thing for a couple of states in the West where it would be really dark, and if we didn't mess with the clocks. But you know what, Colorado, I think you should be on your own because the rest of us are like right up to here, man. It's just like, anyway. So Eastern Daylight Time, Monday, Wednesday, Friday, noon to 2. You can call me and we'll get you fixed up. Okay. So this week, week 10, now throughout the entirety of the semester, we have been looking at quantitative research purely from a sort of a definitional perspective. What is it? What does this term mean? How does it work? At last, I know you've been waiting for this. At last, you get to try your hand at some actual quantitative research. So for week 10, I'll give you, I give you the instructions, but make sure you look in the course content folder. And I've got a data table there that lays out a big study, the results of data gathered from a big study, like 1.4 million people who had COVID and whether or not they had a severe outcome, meaning whether it was worse than just, a common cold, or there was something that required intervention, hospitalization, placement in the ICU, ventilator rate, or worse, the very tail end of severe outcome, death. And on that table, you're going to see the data, the raw data between age groups, comorbidities, and if you don't know what that is, don't worry, I'll explain it to you in the sheet that you get, and then severe outcomes. And I've given you a link to a simple, straightforward regression analysis calculator that will let you plug in the numbers, and then I've asked you a couple of questions. So when you get to question 10 in the discussion board, and if you're going, like, wow, where are the readings? Okay, go over into the course content folder, and you will find all of the stuff to do for week 10. And this week, you actually get to do some quantitative research. Okay, and if you have any questions, if it's it's confusing, send me an email or call me during my office hours. All right, let's take a look at week 8. Seems like a long time ago. We're talking now about tests that test the means between two or more events, between two or more populations. Now, remember, when we say means, I'm drawing on my pad here again, okay? What we're talking about is the average of how something comes out when something happens, okay? So we're going to say this is group 1, this is group 2, and then it goes like, yeah, and then the mean is right down the center. Remember, and then here's group 2, yeah, okay? And then the mean is right down the center. Okay, so here's what we're looking at, all right? And for all of the tests we're going to be discussing over the next couple of weeks, all right, all of these tests fit into the category of analysis of variance tests. In other words, what we are interested in is in at least two groups. Now, it can be more. We're going to talk about that. But at least two groups. We want to know when something happens with the two groups. Let's say it's voting patterns between men and women. Let's say it's support for a particular party among people who are athletic, have are in the gym 3 or 4 times a week, as opposed to those who are not. All right, whatever it is, okay. What we're interested in finding out, and this is key. I want you to make sure that you remember this. Is there any statistically significant difference between the means of these two groups? Why are we interested in this? Well, this is the cornerstone answering that question. Is there any statistical difference between the means? It is the cornerstone of much of what we do in quantitative research. That is, we're interested in finding out if when one group encounters a thing and then a different group encounters the same thing, Is there anything significant about the reaction, behavior, outcome of the first group as compared to the second group? Okay, so all of these tests, these analysis of variance, and remember when we say variance, they mean variance, a variant, any variation in the means, fit into this category. So the first one, the sort of the training wheels, the very beginning, the early, they're just one of the most simple tests in which you're testing for variance is called the t-test. So question number one is, what is a t-test and why would a researcher use it? All right, Matthew, I think you went first, so we're going to take you first. A t-test is a structured method of testing two variables to either reject or confirm a hypothesis. Now that's true, but remember, everybody, go right to the answer, okay? So yes, you use it to test a hypothesis, but you can use a lot of other tests to test a hypothesis. The purpose of the t-test is to test the difference between two independent means. Okay, that is true. Now, what I want you to remember, though, is what we're always after is not merely the difference between the means, but we're after the question of, is the difference in the means statistically significant? All right, remember, what do we mean by that? Okay, well, remember, this was like week 7-6, we pointed out that we live in a very structured and ordered material reality. Things happen with almost boringly predictable regularity, right? And when things happen differently than the boring, predictable regularity, then we say, there must be some force acting on that thing, whether it's a person or an object, in addition to the normal forces that construct reality. Okay, how much of that additional force is acting on it? Is it acting on it in the sense that it is significant to change its behavior? This is what we mean by statistically significant. Now, in most quantitative research, all right, I should say in all quantitative research, there is what's called a confidence interval. What is a confidence interval? Confidence interval is what percentage of the time do you expect the thing to behave in the predicted manner, and therefore, if it behaves in the predicted manner, that percentage of the time, you can say there is no force acting on it. Now, there are all kinds of levels of confidence intervals, but sort of the lowest level that you should comfortably work with is 95%. What do we mean by that? That means if you do something in which there's no other force acting on it, 95% of the time that it's done, it should come out as you would predict. For example, if I take this quarter, and it's from, what state is it from? Oh, it looks like it's from Texas. Yay for Texas. If I take this quarter and I flip it heads or tails, and let's say I flip it, I don't know, pick a number, it doesn't matter. I flip it 50 times, 5 times. All right, so that's 250 flips. But each of the 50 times that I flip it, I write down on a piece of paper whether it's heads or tails. I should expect over the course of those 5 sets of 50 flips that the split between heads or tails will be at least 95% of the time. So, in maybe one of the sets, it's not exactly 50-50. Maybe it's like 48-52, 48 heads, 52 tails, okay? And then maybe another time it's like 49 tails, 53 heads. Would that be right? 51 heads, excuse me. Okay, yeah. So there's a little bit of variance, but if averaged all across the number of flips and the number of time I flip them, it would average out to 95%. That's my 95% confidence interval. If it does not, if for some reason it averages out, below 95%, then that tells me there's some other force acting on this quarter. Maybe it's a trick quarter. Maybe I'm using somebody to help me, because I'm busy over here flipping and I'm just calling heads or tails and they're writing it down. Maybe they're writing it down wrong or incorrectly. Maybe they're jacking me and changing heads when I say tails and tails when I say heads, just for the fun of it. There's some force acting on how this comes out. That's the confidence interval. Now, in most of the social sciences, 95% is good enough. In some of the empirical sciences, well, this is political science, empirical science. In some of the physical sciences and the medical sciences, 95% is way too low. So, for instance, in the chemical and pharmaceutical areas, the confidence interval, very, very lowest it's acceptable is 98%. Because, for instance, if you develop a drug and you turn it loose on the market and you say, well, 5% of the population who takes this drug, all of their hair could fall out. Okay. No, not okay. That is never going to work. Well, it will work, but you'll get your pants sued off of you by the lawyers. So you have to have a much, much higher level of the confidence interval, 98% as a minimum, sometimes even higher, to say, okay, people who take this drug, it will affect the condition that we expect it to with no other significant outcomes 98% of the time. And then there may be 2% in which, if you watch commercials about pharmaceutical products, there's the actors and they're having fun, man. They're at the barbecue and they're on the beach and they're doing whatever. And then you get the voiceover. Buy our drug is not for everyone and may cause, and then you start getting the list of effects that are outside of what you predict the drug is going to do. Now, how many of the populace that take this drug are going to be afflicted by those side effects for licensure and safety, and it actually has to be higher than 98%. It's got to be like 1% or less than 1%, or the drug never makes it. So there can be different confidence intervals. Okay. So remember, it was a good answer, Matthew, but remember, everybody, it's not merely a difference between two independent means. Is there a statistical difference between two independent means? Because with a 95% confidence interval, there could be 5% that slops around. Okay. So, for example, using the coin again, we could construct a test in which we take two different coins. All right. And I just happen to have two coins right here. The first one is our Don't Mess with Texas quarter. That doesn't actually say that on there. And then the second one is a two euro coin. I think I got this. Where was I when I got this? Maybe Ireland, France. I don't remember. Anyway. All right. So we have two different coins. Let me get that so it's not reflecting. There we go. U.S. currency, European currency. This one is substantially heavier than this one. If you look at it's even thicker. You see that? The European, the euro, how much thicker it is than the U.S. coin and the quarter. Okay. So it's heavier. So what if we constructed a test in which, just like before, we said we're going to flip this coin 50 times and then 5 flips of 5 sets of 50. 50, writing down heads, tails, do that 1 time, 2 times, 3 times, 4 times, 5 times. Okay. Then we do the same thing with the euro coin. 55 sets of 50 flips. And we record both heads or tails. Then we average it out. All right. What if we wanted to see if the ratio between coming up heads and tails on the euro coin, because it's heavier, and it's got this funky center in it with, it's made of a different metal. It's actually 2 pieces. You can see it, as opposed to the Don't Mess with Texas solid quarter. All right. What if we wanted to see if there was any difference in the means, the average, statistically significant difference between flipping a euro coin and flipping a U.S. coin, because weigh's different, shape different. Then we would run a t-test. So we have 2 different things, coins, subject to the same event, flippery. That is a t-test. And a t-test will tell us if there is a statistically significant difference between the outcome of the flip of the coin. All right. And I haven't done it, so I can't tell you if there is or not. Okay. Question number 2. Go online and find any study process or procedure in which someone has used a t-test, post a link, and briefly explain to the class the example and why a t-test was used. Okay, so I gave you a link to how Guinness beer was made because they wanted to make sure that it had the same flavor and the same bitterness batch after batch. So to get that, they make a couple of batches, test their bitterness level, take their means, and average them together. All right, Richard. The t-test that I selected is a test review of agricultural innovation program that tests several agricultural methods. For example, in a situation, 2 livestock researchers had 20 cows, which he randomly divided into 2 groups. So nothing, nothing like all the big cows over here and all the little ones over here and all the spotted ones and the non-spotted. He's like, nope, just randomly decide, just go down the line, 1, 2, 1, 2, 1, 2, and split them up. One group received a feed supplement and the other one did not. So we have cows in 2 different groups being subject to the same event. Food or no food, okay? Body weight is measured for both groups before the start of the study and after 6 months. The researcher identified that the null hypothesis of the body weight of the cattle receiving the supplement was greater than the cattle receiving no supplement. Okay, so you got it right except for this last bit, the null hypothesis of the body weight of the cattle receiving the supplement. Now, this is a good answer, Richard. But I want you, everybody, when you pull this stuff out, when you pull these terms out, make sure they make sense to you. And if I called you up and said, please explain to me what you mean when you say the researcher identified that the null hypothesis of the body weight of the cattle receiving the supplement was greater than the cattle receiving no supplement. Explain that to me. Because there's a little bit of a word jumble here. Okay. Remember, statistical speak is kind of its own language. Okay. So, the hypothesis of something like this would be, we hypothesize, and we would say, I'm writing on my tablet again, we would say H1, and we would say cows who are fed, we'll just use capital S for supplement, will weigh more than cows who, you say who with a cow? That, okay? That's not a who. That are not. Okay. And we should insert here by way of language after 6 weeks. Okay, so here's our hypothesis. Hypothesis number 1. Cows, not who, that, okay, are fed S is our supplement, will weigh more than cows that are not after 6 weeks, after 6 weeks of feed. Okay, that's the hypothesis. If it turns out that the cows, so we feed them, we weigh them, then we take their average, and then we compare their average in a t-test to see if there's a statistically significant difference. Not just any difference, because let's say, we divided the cows up randomly. And let's say it just happened that in our herd of 20 cows, there were 3 they are munch machines. They eat everything in sight all the time, right? Test or no test. And those 3 end up in the non-supplement group. And they tend to pack on the pounds much more than their other fellow cows, cow mates. I don't know what the word is. Anyway, all right. And so they're over there in the non-supplement group and they're munching away and they're getting fat and happy like a fat, happy cow. So when you get the total weight of the non-supplement group, the 3 that happen to land in it just by chance has pushed that weight up. And then there is the supplement group that's munching away. So there could be a difference in the means, but is it statistically significant? It doesn't have anything to do with supplement. That's a t-test. Now, if the hypothesis turns out the way you predicted, that is the cows that get the supplement after 6 weeks or 6 weeks of supplement, whatever you like, will weigh more than the cows that don't, the hypothesis is supported. If it turns out that there is no statistical significance between the cows who got a supplement and what they weighed and the cows who did not get a supplement. In statistical speech, you do not say the hypothesis is not supported. Instead, you say the null hypothesis is supported. Why do you do that? Just because you do. Okay. And it's very German, okay, in looking at it. So in German, you would say, I'm writing my pad again. If you wanted to say that's a man, das ist ein Mann. Okay, if you wanted to say that's not a man, so if you wanted to say that's a man, you'd say das ist ein Mann. That's a man. Okay. If you wanted to say, let's say you were pointing to a woman and you want to say that's not a man, you would say das ist ein Mann nicht. That is a man not. So the hypothesis is supported not. See? Null hypothesis. All right. So if that's what you meant, Richard, then you got it. But make sure that you could explain back to someone who said, well, what does that mean when you grab this language? Because, we're going to have a final exam. And if you know the terms, then, wham, bam, bam, you'll crush it. Okay, question number 3. What is the simplest type of ANOVA? Why would a researcher use it instead of a t-test? All right, Matthew, you were crushing it this week. You went first, so we'll take you first. According to the video posted on week 8 course content page, the simplest ANOVA is a single factorial without measurement and repetition, also known as a one-way analysis of variance, ANOVA. Okay, a couple of terms here to break down. Repetition meaning we don't measure the same group twice for different things. There's only one measurement, okay? And one way meaning we're only asking a question about this event to this event, not this event to this event. So we're only asking a question about, say, flippage to outcome, not outcome to flippage. All right? Or cattle supplement to weight, not weight to cattle supplement, because maybe fat cows prefer the supplement. Okay? Why would that be? I got no idea. But that's what we mean when we say one-way analysis of variance. The one-way method is used to determine if statistical significant difference exists between 3 or more groups. Exactly, Matthew. A researcher would utilize an ANOVA if 3 or more samples exist, as the t-test is designed to test independent means of only 2. Correct. So if you have more than 2, let's say that you have, you divide those cows into 3 groups, and you'd have to find some logical reason. Let's say you start with, you divide them into groups according to the 3 groups according to their weight. Skinny cows, regular cows, and fat cows. And if they're each given a supplement, is there any statistically significant difference in the amount of weight that they gain? So if they start really skinny, will they put on, relative to their starting weight, will they put on more than a cow that's already fat? Okay. So you would find that out. That's how you would use a one-way ANOVA. All right. And you get extra bonus points for this question if you were able to figure out what the very helpful woman who did the video meant when she kept saying categories, instead of categories. That cracked me up. It still cracks me up. Categories, as in something that's horrific, gory. Category. All right, number 4. Enough of me. Does an ANOVA tell us in which direction the effect of a causal relationship is running? And answering the question, describe a hypothetical situation to support your answer. Timothy, week 8 course content video explicitly explains one way ANOVA does not provide direction of causal relationship. National female soccer team will perform better than the male soccer team. Okay, that's your hypothesis. Okay, now that's good, but what I wanted is, how is this representative of an ANOVA not predicting the direction? Okay, which is causing which? Not exactly. All right. I mean, because you're saying will perform better. And, remember, you should have 3 and not just 2, because now you're looking at a t-test. Okay. But back to the point. If to get to a test that tells you about a direction, that is, this is causing, in this way, you need to get to a regression analysis, which is what we're going to be doing in week 10. So things like t-tests and ANOVA, they don't tell you which way it's running. So, for instance, I did a t-test once in which I looked at the difference, if there was any statistically significant difference between men and women whose faith were strengthened by watching worship videos. Okay. And was there any statistically significant difference between the average reported strengthening of their faith against the average number of videos? And the answer to the hypothesis, my hypothesis was there's no difference, and the hypothesis was supported. There was no statistical difference between men and women. Okay, now, what this doesn't tell me, when I'm asking the question, I'm asking somebody, do you watch praise and worship videos? Have you found your faith strengthened? It doesn't tell me if people who watch videos have their faith strengthened, or people whose faith are strengthened watch more videos. Can't tell from running an ANOVA or a t-test for that matter. Have to use something called a regression analysis to establish the direction, which is what we're going to talk about in week 10. And you actually get to do a little regression analysis on your own. Okay. All right, everybody, have a fantastic week. Remember, take a look at your test. If you have any questions, shoot me an email. If I've asked, that we can connect and chat on your paper, please reach out and let me know what time is good for you. Okay. And I will accommodate it. And then if you have any problems, because I know we've dealt, in the hypothetical here about these statistical concepts. If you have any problems wrapping your head around this regression analysis, again, send an email to me and we will get you taken care of. Okay. I'm thinking about you. I'm praying for you. And I hope you have a fantastic week. I'll see you on Blackboard. Bye-bye.